In this lecture, we're going to cover section 4.2, logarithmic functions. The first page starts with the definition of a logarithmic function. This may look familiar to you. I feel like at some points or another, you had to evaluate logs. I think sometimes when students see the word log, they get a little nervous because I think it's hard sometimes to understand, what when you plug into the calculator, let's say log of 100, what the calculator is giving you, right? Like what are we actually asking for, in other words, when we press the log button on the calculator? So that's what I'm going to explain first. So classic notation is y equals log base b of x. So that's how we say that, where x is greater than 0, so x is positive, and b is also greater than 0, and b can't be equal to 1, or else y would be equal to 1. So we have the function f of x equals log base b of x. We call that the logarithmic function with base b. All a log is an exponent. And I think once you realize that, it becomes easier to evaluate log statements once you make that connection. So when a log is in logarithmic form, it's going to look like this. We're going to have y equals log base b of x, where y is the exponent and b is the base. So in other words, if we were to write this in exponent form, really what we're asking for when we ask the calculator to evaluate a log statement, we're trying to figure out, okay, with base b, what would I have to raise that to? What exponent in order to give me x? That's really what the calculator is doing when we use that function. So for example, if I have log base 2 of 8, and I want to say, okay, what is that equal to? Instead of just going right to the calculator, and typing in log base 2 of 8, I want you to understand what we're actually asking the calculator to do for us. We're asking for an exponent. The answer to a log is an exponent. So what power would I have to raise 2 to get 8? That's really what the answer is. It's the exponent. 2 is the base. And the question is, what power would we have to raise 2 to get x, which is 8? So in this case, y would be equal to 3, right? 2 to the third is equal to 8. So log base 2 of 8 is equal to 3. Now, obviously, we're not going to be able to do all of them in our head. I made up one that you would know the answer to. So let's practice changing from logarithmic to exponential form and exponential to logarithmic form. So first, in example 1, I want to write each equation in its equivalent exponential form. So I'm going to write it again up here, just so we have it in front of us. So if I have log base b of x is equal to y, this is equivalent to writing it as b, base b, to the exponent, which is y, equals x. One's log form, so the form on the left is log form, and then the form on the right is exponent form. So we could write a log expression as an exponential expression and vice versa. So let's look at A, for example 1. I'm not evaluating anything. I just want to write each equation in its equivalent exponential form. So remember, it's base to the y power equals x. So in this case, this is going to be 7 to the third power equals x. That's how we would write an equivalent exponential statement. For b, we have 2 equals log base b of 25. So in order to write an equivalent exponential statement, take the base b, raise it to the exponent, which is 2, and set that equal to x, which is 25. So now that's an equivalent statement. B squared equals 25. And we'll do one more. Look at C. So log base 4 of 26 is equal to y. So we're taking the base 4, raising it to y, which is the exponent, and that equals x, which is 26. So 4 to the y equals 26. So now let's go the other way around. So now let's go from exponential form. Sorry, I had to think for a minute. So we're in exponential form, and now we're going to the equivalent logarithmic form. So 2 to the 5th equals x, right, in A. So we have log base, my base is 2, right, of x equals the exponent, which is 5 in this case. So those two are equivalent expressions. If we look at B, I have b to the 3rd equals 27. So let's write that in log form. So we say log base, which in this case is b, right? The base is b, of x, which is 27. And that equals the exponent, which is 3. And we'll do one more. So we have base e in this case, e to the y is equal to 33. So we have log base e, because that's the base, right, of 33 equals the exponent, which is y in this case. So that's how we change from exponential to logarithmic form. And then above, we went from logarithmic to exponential form. And these are going to be helpful down the road when we start solving equations that involve exponents and logs. So now let's talk about evaluating logs. So look at example 3. A says, what is log base 10 of 100? So in other words, I'm asking, remember, the answer to a log is just the exponent. What would I have to raise the base to in order to get x, which is 100 in this case, and the base is 10. So in other words, so I think it makes sense to write this in exponent form because then we'll be able to see the answer. So the base to the what power, right? So that's the question mark, is going to give us 100. So 10 to the what power equals 100. And instead of a question mark, let's just call this y. So 10 to the y equals 100. So y equals 2, right? Because 10 squared is equal to 100. So the answer to log base 10 of 100 is 2. So for B, we have log base 2 of 8. We want to know what that's equal to. So we'll just set it equal to y. So if I rewrite this, this is the same thing as base 2 to the exponent y has to equal 8. So 2 to the what power is 8? And that's 3, right? So in this case, the answer is 3. C, we have log base 5 of 1 over 125. We can have a fraction, so x could be a fraction. So let's write this in exponent form. Set this equal to y. So we have 5, that's my base, right, to the y is equal to x, which is 1 over 125. Now, I'm looking at this and I'm thinking, okay, maybe we're dealing with a negative exponent here because the only way that I'm going to be able to take 5 and raise it to a power and get a fraction is if my exponent's negative. Because remember, if I want to evaluate a to the negative n, that's equal to 1 over a to the positive n, right? We have the reciprocal. The reciprocal of 1 over 125 is 125, and 5 to the third is 125, right? But this isn't 125, it's 1 over 125. So y is going to be equal to -3, right? Because 5 to the -3 equals 1 over 5 to the +3, which is 1 over 125. So D, we have log base 36 of 6. Let's set that equal to y and write it in exponent form. So 36 to the y power equals 6. Now I don't have a fraction this time, and I'm looking at 36 and 6, and what's the relationship? Well, 6 is the square root of 36, right? And remember, we can write the square root of something, and we learned this back in chapter P. So if I take the square root of x, remember, that's the same thing as x to the 1/2 power, right? Same thing. Because remember, n, or my index, is 2, and x is being raised to 1. Remember, we learned this? I think this was section P3 with the radicals. So I'm thinking, okay, 36 to the 1/2 is the square root of 36, right? And the square root of 36 is 6. So y is equal to 1/2, because 36 to the 1/2 is the same thing as the square root of 36, which is 6. And let's do one more. So log base 3 of the 7th root of 3. And another way to write the 7th root of 3, we were just talking about it, right? That's like 3 to the 1, and n is 7. Let me just write this a little bit further away from the radical. This is the same thing as 3 to the 1/7. So really what we're trying to figure out is base 3 to the y has to give me the 7th root of 3, right? But another way to write the 7th root of 3, we said, is 3 to the 1/7. So what does y have to be such that 3 to the y equals 3 to the 1/7? Well, it has to be 1/7, right? Y is equal to 1/7. So I think it's important that example 3, we evaluated all these logs without a calculator. I'm going to talk about the calculator later, because I want you to understand the definition of a log first. And the more we do these kind of practice questions, the more you won't have to rely on the calculator. Or when you do see a log statement, you're not going to get panicked or think back to previous experiences that you had with logs and, start telling yourself, oh, I don't know what that means. Now you know what it means, right? When we see a log statement, we could just rewrite it as an exponential statement, and then it becomes easier to evaluate. Sometimes we're not going to be able to do it in our head. We have to use the calculator. Basic properties involving 1. So this we'll see. So for example, log base b of b is equal to 1, because 1 is the exponent to which b has to be raised to in order to get b, right? So b to the 1 is going to be equal to b. And then if we have log base b of 1, that's going to be equal to 0, because 0 is the exponent to which b must be raised, right? B to the 0, and remember, a to the 0 equals 1. So any base to the 0 is going to be equal to 1. So let's just practice. Look at example 4. So let's evaluate log base 9 of 9. This is just going to be equal to 1, because 9 to the first power gives us 9. Log base 8 of 1. So in other words, 8 to the what power is going to give me 1? 0, right? C, I have log base 3 of 3. So again, 3 to the what power is going to give me 3? It's going to be 1. And we'll do one more, D. Log base 4 of 1 is going to equal 0, right? Because 4 to the 0 equals 1. So those are the basic log properties involving 1. There's also inverse properties of logs. So for example, if we look at this first one that I just highlighted, log base b of b to the x is just going to be equal to x. Because remember, the definition of a log is what's the exponent that we would have to raise the base to get this expression. So we would have to take b and raise it to the x in order to get b to the x. So that's that property. And then the second inverse property, which I'm highlighting, says if I have base b and I raise it to the log base b of x, then the result is just going to be x. So let's practice. So let's look at example 5. So A, we have log base 7 of 7 to the 8th power. So this is just going to be equal to 8. Because 7 to the 8th equals 7 to the 8th. B, we have 3 to the log base 3 of 17. This is going to be equal to 17. Because look, if I were to rewrite this expression, because it's in exponent form right now, right? We have base 3, but if I were to write it as a log, I would have log base 3 of 17 equals the exponent, which is log base 3 of 17. They're equal. And then C, we have log base 5 of 5 to the 3rd. And that's going to equal 3. Because 5 raised to the 3rd equals 5 to the 3rd. So let's look at the graph of log x. So if we were to graph log x in our graphing calculators, we're going to get a graph like this. So notice this graph gets closer and closer and closer to the y-axis, but it's never going to touch. And then it's going to increase towards positive infinity in both directions. So since this graph never touches the y-axis, it just gets closer and closer and closer to the y-axis. The domain, you know, what are all the possible values of x? It's anything greater than 0, so 0 to infinity. And then the range is going to be all real numbers because this function approaches negative infinity and then positive infinity in the y direction. And notice this graph passes through the point 1, 0. So all graphs of log functions in the form y equals log base b of x is going to pass through the point 1, 0. Because f of 1, which is equal to log base b of 1, is equal to 0, because b to the 0 is equal to 1. So that would be your x-intercept. And remember, there's no y-intercept. It's not going to cross the y-axis. So the fact that the log base b approaches but doesn't touch the y-axis, we say that the y-axis is a vertical asymptote. So it's like an imaginary vertical line that the graph will never cross or never touch. So those are the properties of our log function. Now, when we see log x, because it is possible to see log of 10 or log of 27, right? Plenty of times you guys have seen a log statement with no base written out. When we see a log written in this form, we assume that it's the common log where the base is 10. So if the base isn't written, the assumption is that it's 10. So whenever we see y equals log x, the base is 10. We don't have to write the 10. If the base is anything else, then we have to write it. So for example, look at example 6a, log of 100. I don't see a base there, so I know, okay, it's 10. So 10 to the what power gives me 100? It's 2, right? So log of 100 is 2. And I want you guys to see how we do that in the calculator. You might be familiar with the log function, but if you're not, we'll do this together. So I'm sharing my calculator right now. Your log function is halfway down the first column. It's highlighted in red now. This is the common log. So if I want to find the log of 100, I just type in 100 and then enter, and we should get 2. So the calculator is giving the exponent that we would have to raise the base to get x. Now, not all these we're going to be able to do in our head. So look at B. This is log of 20. So really there's a 10 there, right? So it's saying, okay, 10 to the what power, y, will give us 20. Well, 10 to the first power is 10, but 10 to the second power is 100. So it has to be somewhere between 1 and 2, the exponent. We're not going to do that in our head. This is the case where we'd use the calculator. So let's type in log of 20, but it should be 1 point something because it's going to be between 1 and 2. So let's type in log of 20 and we get 1.30. So we said to go to 2 decimal places. So this is 1.30. And then we'll do one more for practice. So log of 12. So in other words, 10 to the what power is going to give us 12. And again, it's going to be 1 point something. So type in log of 12. And we get to 2 decimal places, 1.08. Let's do a word problem. Example 7 says the percentage of adult height attained by a boy who's X years old can be modeled by the function f of x equals 29 plus 48.8 times the log of x plus 1, where x represents the boy's age from 5 to 15. So that's the input, x, which is age. And then if we plug in a value of x into this model, in other words, then we'll get f of x, which is the percentage of his adult height. So we can kind of predict the adult height of a boy who's X years old. That's what this model represents. So the question is approximately what percentage of his adult height has a boy attained at age 10? So we want to know, what is the output? What is the height, or f of x, when the boy is 10 years old, when x is 10? So we want to find f of 10 because x is his age. So we're going to plug 10 into the function. So we're going to get 29 plus 48.8 times the log of 10 plus 1. And that we could go ahead and plug into the calculator. And let me just write this down before I go to the other screen. So we have 29 plus 48.8 times the log of 10 plus 1, which really is just 11, right? So over to the calculator. So we have 29 plus 48.8 times the log, so log of 11. And we get 79.82. Which is about 80%, right? We're predicting the percent of the adult height attained by a boy who's 10 years old. So, but by the time the boy is 10 years old, he's attained about 80% of his adult height. So that's an example of, using a logarithmic equation or function to model height in terms of a boy's age, if the boy's between 5 and 15 years old. So now let's talk about natural logs. You have two log functions on your calculator. So you have the log, the one that we were just working with, but you also have ln, which is the natural log. Whenever we're speaking of the natural log, the base is e. And we spoke about the base e in the previous section. So remember, e is an irrational number and it's equal to about 2.72. So e is just a number. So whenever we see the ln now, we're going to assume, and you know what? This is, so you see how here we have log base e of x. Typically, whenever we have base e, we use the natural log. So we would say the ln of x, and the assumption is that the base is e. So for example, 8, evaluate the following log statements. Let's go to decimal places again. So you see how we have the natural log of 3, and I want to know what it's equal to. So in other words, this is base e now because it's natural log. So e to the what power gives me 3. So it's that, remember, e is about 2.72. So 2.72 to the what power is going to give us 3. And we could have the calculator do that for us. So now we're going to press ln, which is below log. So that's the natural log, and we want to type in 3. So the natural log of 3 is going to be to two places about 1.10. B, we have the natural log of 10. So e to the what power is going to give us 10. So let's type in natural log now of 10. It's about 2.30. We'll do one more for practice. So natural log of 12. E to the what power is going to give us 12. So natural log of 12 to two decimal places is 2.48. So that's the difference between the natural log and the common log. Common log, we use log. Assumption is base 10. And then if we see ln of x, that's the natural log, and then the base is e. And let's do a word problem where we use the natural log just for practice. So last example in this section, example 9, says when the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 times the natural log of x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use this function to find the temperature increase to the nearest degree after 30 minutes. So this function, I don't know why this is doing that. Let's try this again. There we go. So this function f of x equals 13.4 times the natural log of x minus 11.6 gives us the temperature increase in degrees Fahrenheit after X amount of minutes. So we want to predict the temperature increase after 30 minutes. So in this case, X is 30. So we want to find the value of the function when X is 30. In other words, f of 30. So that's going to be equal to 13.4 times the natural log of X, but we're replacing it with 30, and then minus 11.6. And that we could plug into the calculator. So let's do that together. So we have 13.4 now times the natural log of 30. You have to close the parentheses, very important, because now we're subtracting 11.6. And we get 33.98. And I believe it said to go to the nearest degree, which would be 34. Yeah, to the nearest degree. So this is going to be about 34 degrees. So that's going to be the temperature increase after 30 minutes, about 34 degrees. I don't like how that 4 looks. Looks kind of like a 9. There we go, 34 degrees. So that wraps up section 4.2. In the next video, we'll cover section 4.3.